Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this haloalkanes and haloarenes. In the previous video, we have discussed the nature of CX bond in haloalkanes. Okay, and in the present video, we will discuss nature of CX bond in haloarenes. So why we are discussing, because it has lot of difference even though both are CX bond only. Okay, so that we will see nature of CX bond in haloarenes. Prior to going for this, so we'll take one example and try to understand that how it is going to differ from haloalkanes. Okay, see, nature of CX bond is going to differ a lot. Say for example, you can take chloromethane, and if you subject for nucleophilic substitution reaction by using aqueous NaOH, then at normal conditions, means at room temperature, it is going to give CS3OH plus NaCl aqueous. Similarly, if you take chlorobenzene and if you try to get the product, okay, plus aqueous NaOH under room temperature, this reaction will not occur to give you the phenol. Okay, so what is the reason for that? Here also it is CX bond or CCl. Here also CCl bond is there, but still it is not going to, or it is reluctant to give phenol under the room temperature. Okay, so but this reaction may happen when you heat around 300 degrees Celsius. Why this difference? One reaction occurs at 28 degrees Celsius or at room temperature, but other reaction, okay, so requires a drastic condition that you have to heat around 300 degrees Celsius to bring the same reaction to give this phenol. Okay, so then there must be something different in the nature of the CX bond when compared to haloalkanes. Because of that reason, we are discussing it separately. Okay, so let us look into this. What is the nature of this CX bond in haloarenes? Fine. So we'll see that one. First, we will see some comparative points that you take CH3X, and here we will take okay. So in both the cases, this is CX, this is also CX, but there is a lot of difference in the substrate. So you see here it is, here carbon is the part of benzene ring. We know the nature of benzene ring, how it is. And here the carbon is free carbon, or it is sp3 hybrid carbon. Here it is sp2 hybrid carbon. This makes a lot of difference. Okay. At the first site, it is going to make the difference. And the second important thing is, we know that the non-binding pairs on the halo group, okay, here are in conjugation with the pi system of the benzene ring. Okay, these non-bonding pair, single bond, double bond, single bond, double bond. So therefore, they are in conjugation. Whereas here, such conjugation we are not going to see. There is no delocalization of the electrons. This makes a lot of difference that what happens, this CX bond will acquire partial double bond character. Okay. Partial double bond character between CX bond. Here it is not having such facility that it can form the partial double bond character. So because of this reason, the breaking of this bond is very difficult, and hence we need a drastic condition to bring nucleophilic substitution reaction in haloarenes. So this partial double bond character, how we can justify, so that we can justify drawing resonating structures. So let us look into that. You know that there are three non-bonding pairs are present in the case of halo group. So when you look into these resonating structures, out of those three structures are going to represent carbon halo group double bond. So this implies that the CX bond is more stronger than compared to the CX bond in the case of haloalkanes. So therefore, the breaking of this bond is very difficult. Okay, this is one part. And the second part is even if you break that bond, then what happens? The formed cation is there, no? So benzene cation. So that benzene cation is highly unstable, so therefore recombines with the halo group, and hence it will not allow for the nucleophilic substitution reaction under normal conditions. In most of the cases, they are going to ask this question that why haloalkanes are readily undergoing nucleophilic substitution reaction but not your haloarenes. So the reason is that the partial double bond character of the CX bond. And another important thing, you should make sure that, of course, the CX bond by inductive effect, by minus I effect, the electrons are pulled by the chlorine atom. From one side, it is going to pull the electrons via sigma bonds, and one side it releases electron into the ring, okay, via conjugated pi system, right? So this is how the CX bond becomes more difficult to break. Hence, it is more reluctant to undergo nucleophilic substitution reaction. It doesn't mean that it will not undergo nucleophilic substitution reaction, but it occurs under drastic conditions such as you have to maintain 300 degrees Celsius. So all that we have to do. So I hope you have understood what is the meaning of this. Then apart from this, any other aid we can bring into this haloarenes, that it can undergo nucleophilic substitution little mild conditions. Okay, so that we can do by substituting this ortho and para position with electron withdrawing groups. Okay, suppose if you substitute electron withdrawing group on these two positions, then the nucleophilic substitution of halo group with other group can be brought under moderate conditions. We cannot say that under complete mild conditions, under moderate conditions we can bring. So we will see that how it is going to happen. Okay, so let us see that one. The nucleophilic substitution reaction, such as if you take if you take chlorobenzene, say for plus aqueous NaOH, you will take one example. At 300 degrees Celsius, you are expected to heat to bring the nucleophilic substitution. Okay, like this we are going to get. Now the same reaction, if you carry out in presence of electron withdrawing group at ortho position, aqueous NaOH. Okay, if you heat around 200 degrees Celsius, we can readily bring the change. Okay, similarly, even you can bring by taking nitro group at para position. So same around 200 degrees Celsius, if you heat, you will end with the product. Nucleophilic substituted product we are going to get. And one thing you should remember, this reaction occurs by bimolecular mechanism, that is SN2 mechanism it follows. Okay, attacking group attacks first and followed by leaving group leaves later. Okay, and that is being promoted by these electron withdrawing groups. These electron withdrawing groups, what they do, so they abstract the pi bond and make this carbon as carbocation, and then readily the nucleophile is going to attack at this position, and then it will delocalize, and the elimination of the Cl group occurs readily. Okay, so that is how the substituent group at ortho, electron withdrawing substituent group or ring deactivating group at ortho and para position will promote nucleophilic substitution reaction in haloarenes. I hope you have understood what is the nature of the CX bond in haloarenes and how it undergoes the nucleophilic substitution reaction when compared to haloalkanes, under what conditions, and how the electron withdrawing group is going to influence the substitution reaction in haloarenes. Thank you for watching, and please don't forget to subscribe our channel. Thank you.